A wheel has a moment of inertia of 500 kilograms meter squared. How much rotational kinetic energy will it have if it's rotating at 25 radians per second? Well, we know that I equals 500. We know that omega is 25, and our formula for rotated kinetic energy, or K rod, is equal to 1/2 I omega squared. That'd be 1/2 times our I is 500 times omega, which is 25, but squared. So 1/2 times 500 times 25 squared. Put that in a calculator, we get 156,250. This is energy, so our unit is joules. What is the angular velocity, so omega is what we're looking for, when it has 2.25 times 10 to the 5th joules of rotational kinetic energy, so of K rod? Again, our I is 500 because this is still a part of number 1, and K is equal to, or K rod is equal to 1/2 I omega squared. .25 times 10 to the 5th is equal to 1/2 times 500 times omega squared. I would multiply both sides by 2 to get rid of the 1/2. Then I would divide both sides by 500, leaving omega squared by itself. Once we put that into a calculator, we would have 900 is equal to omega squared. Don't forget we're looking for omega, not omega squared, so we're going to take the square root of 900, and that should be 30 radians per second, the unit of omega, or rotational velocity. A wheel has a mass of 0.5 kilograms. So mass is 0.5 kilograms. The radius is 0.25 meters. It rolls such the center of mass of the wheel has a velocity of 10 meters per second. So we know the linear velocity is 10 meters per second. Calculate the angular velocity of the wheel. Angular velocity is the linear velocity divided by the radius. So still, I'm summarizing up my information, got it off in the edge there. 10 divided by 0.25. Just taking our givens with our formula, and we get 40 radians per second. Calculate the translational kinetic energy of the wheel. Translational kinetic energy is regular kinetic energy, K. K equals 1/2 mv squared. So 1/2 times the mass of 0.5 times the translational linear regular velocity of 10 squared though. 1/2 times 0.5 times 10 squared is 25 joules. Calculate the rotational kinetic energy of the wheel. Rotational kinetic energy is 1/2 I omega squared. In this case, we're going to treat the wheel to be like a tire, so it's a ring. So I is equal to mr squared. K rod, or rotational kinetic energy, would then be 1/2 times the I is mr squared times omega squared. So our K rod would be 1/2 times 0.5 times 0.25 squared times 40 squared. Because we know what the mass is, we know what the radius is, we know what omega is. Put that into a calculator and we get 25. And again, 25 joules because we're measuring energy. Calculate the kinetic energy of the wheel by summing the two kinetic energies together. So total kinetic energy. Total kinetic energy would be our translational kinetic energy plus our rotational kinetic energy. 25 plus 25 would get us 50 joules. A solid spherical marble of mass 0.2 kilograms, so we know mass is 0.2 kilograms, and because it's a solid sphere, we know I is 2/5 mr squared. Radius is 0.05 meters. It's set into a spring-loaded projectile launcher, so we know our initial energy is going to come from spring potential energy. Spring constant is 1,000. It's compressed, so the displacement of the spring is 0.25 meters. Calculate the velocity, so we're looking for linear v, translational v, regular velocity of the marble immediately after it's launched, assuming the marble slides out of the launcher without rolling, so it's only moving linearly. So we're going to say our initial energy, E naught, is equal to our final energy, E. Our initial energy is spring potential energy, and our final energy is just translational kinetic energy. US is equal to K. 1/2 kx squared is equal to 1/2 mv squared. The 1/2s will cancel out. And we're left with kx squared over mass is equal to v squared. Now's a good time to put numbers in, if any. 1,000 times 0.25 squared, because k times x squared, divided by the mass 0.2, is equal to v squared. Put that in my calculator. I got 312.5 is equal to v squared. Taking the square root of that, I don't want to know v squared, I want to know v. Square root at 17.68 meters per second, my units for translational velocity. But if the marble were to roll out without slipping out of the launcher, it's moving left or right, it has kinetic energy. It's rolling. Slipping would be you hit the gas on your car on ice and your wheels spin and they don't go anywhere. That's slipping. So it's rolling, it's not slipping. Nothing we're going to do, I think, is going to slip. So now we've got US, our initial kinetic potential energy from the spring is equal to K plus K rod. 1/2 kx squared is equal to K is 1/2 mv squared. K rod is 1/2 I omega squared. This is a solid sphere, so we're going to have 1/2 kx squared is equal to 1/2 mv squared plus 1/2. The I is 2/5 mr squared, and then the omega squared could be changed for v over r, but then squaring it, v squared over r squared. Because remember, omega is v over r. We can cancel out the 1/2s, and we can cancel on the far right side, we can get rid of the r squares because we've got times r squared and then divided by r squared. We end up with kx squared is equal to mv squared plus 2/5 mv squared. Well, I've got 1 mv squared and I've got 2/5 mv squared. I pretty much have 7/5 mv squared. I'm trying to solve for v, so I'm going to multiply both sides by 5/7 to get rid of the fraction on the other side. Multiply both sides by 5 and then divide by 7 to bring the fraction over. You get 5/7 times kx squared over m is equal to v squared. Plug in our numbers. 5/7 times 1,000 times 0.25 squared divided by 0.2 is equal to v squared. Put that into a calculator, we get 223.21 is equal to v squared. We don't want v squared, we want v. So square root, and you get 14.94 meters per second is the translational velocity. A block of mass m slides up an incline shown above with an initial speed of v naught. The incline's frictionless, so we know the initial energy is equal to the final energy. So E naught is equal to E. Our initial energy is kinetic energy, which is equal to the final energy of gravitational potential. 1/2 mv squared is equal to mgh. Masses cancel on each side. Now we're just going to solve for the height, which would be dividing the g to the other side, v naught squared over 2g. If the incline is rough with coefficient of sliding friction with mu, determine the maximum height to which the block would rise. We're still going to say initial energy is equal to final energy, and we've got our kinetic energy is equal to the gravitational potential plus the work done by non-conservative forces, because that's going to take away from our initial energy. We have K is equal to UG plus force of friction times the distance that force of friction acted, because you can't just add a force. You have to add a force times a distance so that you get the work done by that force, which is a change of energy. 1/2 mv squared on the left is equal to mgh plus. Now we need to figure out what exactly force of friction, how can we identify it? FF is not a way to do it because those aren't variables they gave us. So let's take a look at the image and draw a free body diagram. I'm going to say mg is going straight down, and then if I change my perspective so the box is horizontal, I've got a component of gravity that's horizontal, a component that is vertical. The horizontal component of gravity would be mg sine of theta. The vertical component would be mg cosine theta, because the vertical is adjacent to that angle, so it's cosine. Force normal is balanced with the vertical component of gravity, so force normal is mg cosine theta. And of course, force of friction is the coefficient times force normal, so coefficient times mg cosine theta. Now we've been able to identify exactly what force of friction is, and we can put that into our formula. 1/2 mv squared is equal to mgh plus coefficient times mg cosine theta, and then we've got that times d, that times the distance that it's going to move along. D is not a variable that they gave us in the problem. It's not a universal constant. What did they give us? They gave us h for height, and they gave us theta for the angle. So we need to use the things they gave us. I'm drawing the picture again over to the side because my free body diagram's is in the way. So if I've got D as the hypotenuse, H is the side, and then the theta, I can say that the sine of the angle is equal to, what do I have? H over D, opposite over hypotenuse. Rearrange this all for D. I've got H over sine theta. So let's put that into our sentence where it's the length, the distance is H over sine theta. Now we're using variables that are legal. Well, if we've got a mass everywhere, can't we cancel the masses? Wouldn't that be something that would be easy to do, simplify our equation? So if we cancel those masses out, we can simplify things a little bit. If we multiply both sides by 2, we could get rid of the fraction on the left. I'm kind of one that likes to get rid of fractions, so if we multiply by 2, we just distributed 2 on the other side. Since it is MGH plus coefficient, I would have 2GH plus 2 coefficient G cosine theta times H over sine theta. Now we're looking to actually get H on one side because we're solving for H. So what I'm going to do is I'm going to go ahead and divide both sides by H. That's going to move it to the left side, eliminate it from the right side. So we'll have V squared over H is equal to 2G plus 2 coefficient times G times what's essentially left over, cosine of theta over sine of theta. And if you remember, I believe cosine of theta over sine of theta, cosine over sine is cotangent. Just to get rid of the fraction, I'm going to use cotangent. 1 over H. So if we were to divide both sides by V squared, 1 over H, 1 over the height is equal to 2G plus 2 coefficient of friction times gravity times the cotangent of theta over V squared. Well, that's 1 over H. So I need to invert it. I want H, not 1 over H. So I've got H is equal to, flip that nasty fraction over, and we've got V squared over 2G plus 2 coefficient times G times cotangent of theta. Is there more than one way to do it? Absolutely. Is this the most disgusting one on the page? Absolutely. This was your challenge problem. If you can do them all but the challenge problem, you're doing pretty darn good. If you can get the challenge problem, I'm pretty darn proud. All right, now we've got a loop, thin loop, so it's basically a ring that's a mass M, radius R, going up a hill. If the incline is rough and the hoop rolls, okay, if it rolls, it's not sliding, right? It's rolling. Friction is going to help us transfer energy from K-rot in and out of K-rot because it's a torque. It allows us to change the angular velocity. If there's no torque, there's no way to change angular velocity, so your K-rot's permanent, whatever it is. Zero, non-zero, it's permanent. So what we're going to say is the initial energy is equal to the final energy. We've got K plus K-rot. It's spinning and moving left to right, and it's going to finish at the top of the hill, not spinning. 1/2 mv squared is equal to 1/2 I omega squared is equal to mgh, just replacing the variables from the formula. 1/2 mv squared plus 1/2. What is the I for the hoop? It is mr squared. What is omega? It's V over R, but it's squared, so V squared over R squared is equal to mgh. We're going to cancel the m's out, and the R squares cancel out as well. Makes things simple. I've got 1/2 V squared plus 1/2 V squared is equal to GH. Well, 1/2 of V squared plus 1/2 of V squared is a whole V squared. So I've got 1 V squared, or V squared, is equal to GH. What are we solving for? I kind of forgot already. For the height, right? So divide G to the other side, V squared, which really should be V naught squared, shouldn't it? Did I fix that? Who knows? V naught squared over G is your H. All right, the last one says the incline is frictionless. Frictionless means there's no torque. K-rot has to remain the same because without a torque, you cannot have an angular acceleration, so your angular velocity is fixed. You're not going to be changing your K-rot. So we're going to start with initial energy is equal to final energy. Our initial energy, well, it's moving left to right and it's spinning, so we've got K plus K-rot is equal to, well, that left to right energy is going to carry me up the hill some, so I've got some UG, but I still have my K-rot because I don't have anything that's going to remove or change that angular velocity. The two K-rots are equal to each other, so I canceled them on both sides, just subtracted them from both sides. I've got K is equal to UG, 1/2 mv squared is equal to mgh, cancel the m's. 1/2 V squared is equal to GH, so then my V naught squared over 2G is my height. And wasn't that loads of fun?